Yes.
Yes, you're golden. Okay, and last Iris talk of the day is by Jonas, and it's an actress, not the Hollywood kind, the kind that's about session types in Iris.
Thank you. Yes, so greetings and welcome to the last talk of the programming logics session. This will be about Actris, which is joint work between myself, Jesper Bengtsson, and Robert Krepes. Now, Actris is a framework for doing, so to speak, session type-based reasoning in separation logic. And that is something we want to use to do reasoning about functional verification of actual model programs. So let me start out by just talking about what actual model programs are. As we all know, writing concurrent programs is hard. The actual model gives us a principled way of writing concurrent software in that it isolates concurrent behavior by treating threads as either services or clients with no shared memory between them. And then instead use message passing to interact and send messages. This is a very permanent method that is used in many state-of-the-art languages such as Erlang, Elixir, Go, and more. The most common way to introduce message passing in your language is to include the three message passing primitives as seen here. You have newChan, which creates a new channel and gives you the two endpoints of the channel. Then there's send, that takes an endpoint and a value to send that value over the channel. And lastly, there's receive, which receives values sent by the other endpoint. An example of a message passing program is the one up here, stating that we first use newChan to create a new channel. Then we fork off a service thread that receives a number, adds 2 to it, and sends it back. And then the client acts as the main thread acts as a client, which uses this service to add 2 to 40, resulting in 42, which is then returned. Now, many variants of message passing exist, but the one that we consider is asynchronous, meaning that whenever you send, you don't have to wait for the other guy to receive. It's order-preserving. Messages are received in the same order that they send, and it's reliable, meaning that messages are never dropped. Right. So what's the problem at hand? Well, Tasharov et al. Said that Tasharov et al. Investigated 15 large-scale Scala distributions and found that 80% of them actually combines the actual model with existing concurrency models, meaning that message passing, while very nice, is not necessarily silver bullet for writing like any concurrent software. So the problem that we find is that we want to do very functional verification of these kind of programs, but no sort of end-all be-all solution exists for doing this sort of reasoning that actually combines message passing with concurrency models. At least no solution that is also dependent and high level, which are properties that we found to be very important for the expressivity of this kind of reasoning. When we say dependent, we mean that protocols can depend on previously sent messages. And when we say high level, it means that we can actually communicate stuff like references, channels, and higher order functions. So the key idea to solving this is to create protocols that are defined, that are sort of akin to session types, and use them as specifications in concurrent separation logic. Now, session types, because it is a type system for channels, meaning that it sort of doubles as a protocol specification, a very simple one at that, as you can see in this example up here, which states that a channel endpoint must first send a natural number, then receive a natural number, and then terminate. With session types, you can ensure safety and session fidelity, meaning that your program will not crash and messages will never be sent wrongly. Now, as for concurrent separation logic, as you're likely familiar, it's a logic for reasoning about concurrent programs with mutable state. As for the mutable state part, there's an example here stating that if you're to store a value in a location, you need ownership of that location. You need to know that it exists. And the result is then that you have actually updated the value. With concurrent separation logic, we then ensure functional correctness. So the contribution of this effort is then Actris, which is now the concurrent separation logic for proving functional correctness of programs that does this combination of message passing and other concurrency paradigms. In doing Actris, we introduce a new notion of dependent separation protocols, which can be thought of as logical session types. We integrate the whole shebang with Iris and its existing concurrency mechanisms. We do verification of various feature-heavy programs, including a variant of the MapReduce algorithm. And we do a full mechanization of the whole thing in Cog, which is open source and available online, so you can go access it and play around with it if you want to. To further specify dependency separation protocol, it is in fact a specification and proof system that allows you to reason about sending references, sending function closures, sending channels over channels, dependent on previous messages, looping protocols, protocol with choice, and sharing channel endpoints. Now this is lots to take in, and it's actually too much to cover in the talk, so I will only sort of cover the following 4 here. Okay, so to give you an idea on what Actris actually is and how we use it, I'm just going to do a tour. Now, the language that we consider is an ML-like language that is extended with concurrency, state, and message passing. Again, the message passing primitives as is previously explained. The example program is the program from the very first slide, and the goal is then to prove that this thing in fact terminates, that this in fact results in the value 42. So if we first consider this program from the point of view of session types, well, session types is a type system where we have 3 primitives at its core. It states that we can either send a value of type t, receive a value of type t, or terminate. An example is again that we can type check a channel endpoint stating that it must first send a natural number, receive a natural number, and terminate. And in session type, we have this notion of duality stating that the dual of a session type is the exact same type where we have flipped all sends to receive and vice versa. This is used in the typing rule for new channels in which we can freely pick a session type so that when we get the 2 endpoints, one endpoint will have that type and the other will have its dual, meaning that whenever one guy sends, the other will receive and vice versa. Now, the rule for send states that we must consume a channel endpoint that is in fact expecting to send, and a type and the type that we actually expect to send. And then we continue as the detail of the protocol. Conversely, for receive, we must consume an endpoint that expects to be receiving, and the result is something of the type that we actually expected to receive, and the tail of the protocol. So with that, we can now revisit our example here. We can choose the session type as follows here, saying we send and receive a natural number, and then we can more or less simply apply the typing system and obtain that we have type safety and session fidelity. The program does not crash. It's sort of fine. However, we cannot show that it results in 42 because we do not have functional correctness. Session types are simply not strong enough for doing something like this. This is why we introduce our dependent separation protocols, which are designed very much to be in style of session types, as you might get the impression here. Where we, in the session type, have our 3 primitives here, we have similar primitives saying that we send, we receive, and we terminate. However, instead of sending and receiving types, we send and receive predicates. In particular, we say that we send or receive a range of logical variables, x's, of type taus, the physical value v, and the predicate p. An example of such a protocol is then the following here, which states that we must first send a logical variable x, a physical value, which is exactly x, and then true, so no restriction on the value. This is exactly the same as we had before with the session type. We just send a natural number. As for the second part of the protocol, we state that we must receive a logical variable y, that exact physical value, and a restriction saying that y is exactly equivalent to x plus 2. So now there's actually a restriction, which is also dependent on the very first value. As for duality, we have the exact same notion as in session types. We simply flip sends and receives. And as for usages, where in session types you would usually type check, we instead have sort of a logical connective in ownership of channel endpoints, which is similar to an ownership you would have over locations. So we usually say you own a location that points to some value. You here say that you own a channel endpoint and that it adheres to the protocol defined by prod. So with the definitions in hand, we can now look into the rules. The rule for new-chan is very similar to that of session types. There is no restriction in the precondition. You can always create a channel. In doing so, you get 2 physical endpoints, where one physical endpoint, where you have ownership of both physical endpoints, one with the protocol that you freely choose, and the other with a dual. When you send, as with session types, you must consume ownership of a channel endpoint that expects to be sending. You need to send the physical value as dictated by the protocol, and you need ownership of the predicate as dictated by the protocol. Now the result of doing this is then the ownership of the tail, which is again exactly sort of similar to session types. Now all this is up to the substitution of an instantiation of the logical variables defined in the protocol, which is this range t here, which you can think of as sort of sending the variables over. Conversely, for receive, we must consume a channel endpoint that expects to be receiving. The result of doing so is a physical value, which is actually the value dictated by the protocol. We obtain the protocol that was sent over the predicate that was sent over the channel, and again the tail of the protocol. Now all of this is up to substitution by this existentially quantified range of variables, which have the same type as the ones dictated by the protocol. This can be thought of as receiving all of the logical variables that was sent. So with these in hand, we can now go back to our example. We can use the protocol from the example and more or less simply apply the rules from the previous slide to actually show that this thing becomes 42. If we just consider the main thread here, we apply the send rule to consume this guy. We just send some natural number. We apply the receive rule on the receive case and show that what we actually get is in fact the first thing that we send, 40 plus 2, which is 42. So we're done. We now have functional correctness. Now, I propose that we actually want to sort of combine this thing with mutable state. Here we're just sending values. So let's just talk a bit about references. We updated our example program to now say that we create a channel. The service will instead now take and receive a location. It will dereference the location, add 2 to it, and then restore the new result. It will then finally send back a notification saying, I'm now done mutating the shared state. In the main thread, we create a reference to 40. We send the location over. We receive the notification back saying, the other guy is now done mutating, so now we can freely dereference it here. So we first receive sort of the ownership of the location from the rule of ref. Then the protocol that we specify says that we send a logical variable, which is a location, a natural number. The physical value is, in fact, the location. And then the predicate is ownership of that location. So we give up the ownership when we send. And then we get back the ownership from the second part of the protocol with the notification, which is why we can then dereference it in the rule for dereferencing to obtain the value, which is, again, 42. So I hope that serves as a good intuition on how to use Actris and ample evidence that it's actually usable. So let's talk a bit about why it actually works. Let's talk about the soundness of Actris. The soundness of Actris is defined as the Hoare triple here, which states that if you, from no precondition, can execute the program E and then show the postcondition phi of the return value, then you have type safety and session fidelity, and you have functional correctness. Now, this soundness is obtained by modeling Actris directly on top of the Iris logical framework. Now, Iris, without going into all the nitty-gritty details, is, of course, a language-independent, high-order, impedicative, concurrent separation logic that is in Coq. And all you need to know is that this is exactly what we need to create Actris. The approach is then to first implement our message passing primitives as a library using lock-protected buffers. We then define the dependent separation protocols using Iris's recursive domain equation solver. And then we can define this channel endpoint ownership using Iris's invariant and ghost state mechanisms. Now, this is quite intricate how it works, and I won't have time to get into it. But you can ask me in the break if you want to see it. It's cool. Lastly, we prove the rules, as seen previously, of Actris directly in Iris, which means that we obtain the soundness of Actris directly as a corollary of Iris's soundness, because everything is just made directly on top of Iris. A benefit of this is then that we can readily reuse all of Iris's support in Coq, all the nice tactic supports and everything else. We get a very, very small Coq mechanization. It's about 2,000 lines of code in total. And most importantly, we readily integrate with all of the concurrency mechanisms that you already know from Iris. To emphasize this last point, we just can quickly consider this example here, where we have a program like before. We create a channel, the service. In the service, we create a new lock, then we race for the lock in order to send 21 over the channel endpoint, while in the main thread, we just receive on the channel endpoint twice and add the values together. In order to prove this kind of program, we define our dependency separation protocol as such, which is recursive. It states that we recurse over a natural number. If the number is 0, then we terminate. Otherwise, we simply send or receive 21. And of course, for this program, we can instantiate that program protocol with true, and we have exactly what we need. Now, the reason why we need to do this sort of recursive protocol is to isolate the behavior that will happen inside the critical sections of the service. As for the proof, well, the main thread follows immediately from the Actris proof rules that you saw previously. In the forked off thread, in the service, we do require some more intricate reasoning with locks. However, the important thing to note is that that reasoning is entirely orthogonal to the reasoning that we do in Actris. It's just treated as any other sort of resource of Iris, which means that we effectively obtain this sort of seamless integration with existing concurrency mechanisms that we wanted from the beginning. So if you think, if you find that interesting and want to know more about that, as well as all the other things that I did not get to cover in this talk, such as the various other features of Actris, all of our case studies, which are distributed merge sorts, distributed load balancer, this MapReduce thing, and more about the definition, the actual definition of our model, well, all that stuff is in the paper and in the mechanization, and of course in my head. So again, please come and talk to me. I'd love to talk more about Actris, and that's all that I have for you. So thank you.
Thank you very much, Jonas. Do we have any audience questions? Okay. Just a second.
So how you treat the recursive type?
Recursion?
Recursive type.
Type?
Yes.
Right.
You don't have recursive type, and also more interesting thing is probably you can encode shared name by reference, I guess.
Mm-hmm.
And however, so recursive type and also subtyping is very important feature of the session types.
Yes.
And so how you come up about, but the recursive type and parametric recursive predicate would be probably more useful.
Yes, so we have recursive dependency variation protocols, and that is because the way that it's defined is again with Iris's recursive domain equation solver. So the recursive occurrence of the protocol, the tail of the protocol, is actually guarded under a layer behind the scenes. So you can use Iris's fixed point to acquire actually logically recursive protocols. In the types, not entirely sure about the difference. Anyway, we can take that offline. So thank you. And just on the other point about subtyping, this is something that we actually have updated in the mechanization after publishing and whatnot. So we do have that, and it was pretty straightforward. So thank you.
Hi, Jonas. That was a nice talk. I have a question exactly about that slide. If I understood correctly, you have this weird forking pattern because you want to hide the lock from the receiving of the channels, right?
Yes.
And this is orthogonal maybe to what all you had said, but couldn't you perhaps envision doing everything with a writers-readers lock in which the receives could know about the lock, but then they are readers, so they don't need to deal with ownership?
So what do you propose again? Sorry?
So you have a parallel composition of everything, but instead of having normal locks, you have reader-writer locks, in which writers synchronized to send a message that the readers can always read.
Right. So, I mean, again, as you also pointed out, like this entire reasoning is orthogonal to Actris. It's just like any other sort of ownership in Iris. So, can it be done with? If it can be done in Iris otherwise, then it can also be done for this thing. So it's like orthogonal to this kind of work. Thank you.
Any more questions? Okay, one more question from me, and then coffee. Just out of curiosity, have you considered what it would mean to extend this to multi-party session times where you have broadcasts instead of end-to-end communication? That might be an unfair question. It's a lot, but...
Some of the ongoing and future work is, in fact, to extend this thing to multi-party session types or multi-party dependent separation protocols. Of course, very different. We have made some considerations, but most of the considerations sort of resulted in headaches, saying that this thing will likely be harder than expected.
Especially because resource transfer, if you have end-to-end communication, then the sender sends to receiver, but in multi-party session types, at least it's not clear to me how the resource to run.
Yes. So there is some ideas, but nothing concrete yet. But thank you.
Very good. Okay, coffee time. Thank you very much.